if you can hear me clearly. Is everyone hearing me clearly? I need every one of you to confirm if, okay, you hear me clearly, right? Thank you so much. Thank you for confirming that. I want to welcome everyone to my lecture today. Of course, today I'm going to walk you through another exciting topic in statistics. But before I get started today, I want to tell everyone I've not been seeing you during my office hour. If my office hour is conflicting, please reach out. If my office hour is conflicting with your schedule, I need you to reach out, okay, because I want to hear from you. Okay, so today I'm actually going to walk you through another exciting topic in statistics. And you know what I'm displaying now. I'm displaying the framework, what we've done so far and what we actually see going to do next. You remember in this semester, I actually started with basic statistics review. Okay, I started from there. Then after there, we move into simple linear regression module. Let me first tell you, I think I want to have a recap today. Let me have a recap before I go into what we have next. Like I said, I started with the basic statistics review, where I actually walk you through some basic statistical terminologies and some basic statistical fundamentals. Something like I walk you through what we call the mean, the variance, and so on like that. And of course, I actually presented different kind of probability distribution, like normal distribution and a t-distribution. And of course, I actually show you, parameters of each distribution. Like, remember, I told you for normal distribution, it is characterized by mean and variance, okay? And for, t-distribution, I think I told you something about the degree of freedom, because in statistical analysis, when we are conducting maybe when we are trying to get what I call statistical inference, where we want to estimate parameter or we want to conduct hypothesis testing about parameter, of course, you actually make use of certain probability distribution. The test statistic at times could be, the one that actually assume a normal distribution, and we could also have the one, that revolve around t-distribution, and that was the reason why initially I actually expose every one of you to basic statistics review. Okay, and I remember I also differentiated between what I call the population mean, the sample mean, the population variance, the sample variance, and so on like that. Now the next after that, we actually talk about the simple linear regression model, okay, a situation where we actually want to characterize relationship between two variables, one continuous and the other one, continuous as well. You basically want to predict, the predictor from, you want to predict the response variable from the predictor. Okay, of course, we actually specify linear regression model with assumptions, and of course, I walk you through each of the assumptions. I remember assumptions of linearity, assumptions of constant variance, assumptions of normality, okay, and so on. Like I think I also mentioned something that has to do with the independence of observation. And of course, I walk you through how to investigate each and every assumption. And I remember I told you that a model is as good as assumption put into a model. I'm going to say that again. Okay, a model is as good as assumption put into a model. So what make a statistical model great is when assumptions underlying the use of the model are not violated. Of course, we have a way to investigate that. Okay, and that was what I was talking about. Diagnostics, diagnostic is more or less like you want to evaluate your model after you've successfully estimated parameters in a linear regression model. Subjecting the model to diagnostic testing actually means you basically want to investigate whether assumption hold or not. And if assumption does not hold, like if there's a violation, of course, we can actually do transformation. You remember that we do transformation. I think I walk you through that, the power transformation. You could have a log transformation or a log, a reciprocal or the square root transformation and so on like that. And of course, the essence of transformation is actually to attain linearity or to attain normality. And of course, we have a way to investigate whether the transformation efforts has worked. Okay, I want you to also remember that. And you know what? We also move away from simple linear regression model where we only have one predictor to multiple linear regression model, okay, where we have more than one predictor variable. I think I told you the other time, the reason why we may want to go beyond simple linear regression model, okay, to multiple linear regression model, because we actually want to improve on the quality of our model. Okay, if we want to improve on the quality of our model, of course, we're basically going to go from a simple linear regression model, that is a situation where you only have one predictor to many predictor. Of course, there's possibility that relationship, there's possibility that a single predictor variable may not be able to explain the variation in the response, and that is the reason why we may want to have more than one predictor. I remember I walked you through one form of this that we call polynomial regression. Okay, the polynomial of degree 2, degree 3, and so on like that. You consider that polynomial because of the fact that relationship between the response variable and the predictor may not be linear one. Maybe you actually need to incorporate a nonlinear effect, which could be a quadratic effect or could be a cubic effect into the linear architecture before you can successfully, capture the curvature in the data set. Okay, and of course so when you are actually talking about the polynomial regression, it means you are adding more regressors into the model. I remember I walked you through an example where we want to predict the daughter's height. Okay, if I know mother's height, can I actually predict the daughter's height? Okay, when I have information about mother's height, okay, can I predict daughter height? Of course, we now realize that probably we needed to incorporate if I have information about maybe the quadratic effect of mother's eye, okay, we can actually, maybe that could actually improve the quality of the model. Of course, then I also consider a situation where we also want to make use of the height of the father. Okay, not only the height of the mother, we also use the height of the father, okay, to predict, what the height of the daughter is going to be. I think I also told you that during my bachelor project, I work on something that has to do with multiple linear regression, where I look at the effect of inflation rate, the exchange rate, and the consumer price index on the gross domestic product of Nigeria. Okay, so in that, I consider three different predators. I look at the effect on the response. Okay, and I remember I walk you through so many examples in this course. I remember I walk you through. I think I started an example that has to do with determining the price of an item in Italian restaurant in New York City. Okay, I remember we have predators the quality of the food, the decoration rating. We also consider the service, and we consider whether the restaurant is located in the east or west of the Fifth Avenue in the New York City. Okay, so in multiple linear regression, I also walk you through what we call variable selection. Before moving to variable selection, I think I also talk about, model fitness and model complexity. I told you when you want to talk about model fitness, we use two criteria that we call the residual sum of squared and R squared. And I told you those are only appropriate for model fitness alone. But if I want to talk about model fitness and model complexity now, okay, you cannot trust your R squared. You cannot rely on the residual sum of squared. And I said we have a brand new set of criteria that can actually be used for such when model complexity is actually being put into consideration. We're basically going to adjust our R squared. We're going to call that adjusted R squared. We're going to talk about AIC. We're going to talk about BIC. And those are the three criteria that we actually use, okay, when we are actually consider model fitness and model complexity. Okay, I just wanted to take note of that. Of course, we could have a situation where we have more than one model, more regression model, and we have that are competing, and we actually want to decide on which one of them is basically going to work great. Of course, I remember I walk you through two different method of selecting a model. I remember I talk about all subset selection, and I also walk you through the stepwise regression. Or you remember I walk you through the stepwise regression, the forward. In the stepwise regression, you have the forward selection. You could do forward selection with the AIC. You could do forward selection with the BIC. You could do backward elimination with the AIC. You could do backward elimination with the BIC. I think I also walk you through how you can actually implement that in R. And I also remember I walk you through situation like you are comparing between the most simplest form of a linear regression model that I actually call intercept model. If you're comparing that with any other form of linear regression model, of course, we make use of F-test, okay? But situation, we are actually comparing two different models, and one is simple and the other one is actually has more predictor variable, so which means you are actually comparing between the simple linear between the simple model and a complicated model. Of course, you actually use a partial F-test that we also call the nested F-test. I think I actually walk you through that. And of course, when you are considering a simple linear regression model or multiple linear regression model, of course, we have to ensure that your response variable that we actually call outcome variable has to be continuous. I believe you know that. Okay. But what of in a situation now? where the response variable is categorical. Okay, when the response variable is categorical, we cannot use linear regression. Of course, I think I demonstrated that to everyone, that there's going to be that, using a linear regression for a categorical response variable will actually lead to what I call a violation of assumption. And you know what? When assumptions are violated, okay, when assumptions are violated, of course, you cannot trust your model, okay? And, I think I walk you through the appropriate model, okay, regression type model that can actually be used when the response variable is categorical. I think I give you an example of that. Response variable is categorical. You apply for student loan. It's either the response is going to be, it's either you are giving or not. Okay. It's either there's a disease or there's no disease. Okay. So, situation like that, when the response variable is categorical, of course, you're actually going to use logistic regression model. Okay, using a linear regression model will not do a great job, because it's going to lead to violation of assumption. And of course, I walk you through in the logistic regression model. I walk you through what we call a simple logistic. I walk you through multiple logistic. Of course, the simple logistic is when you have one predictor variable, and the multiple logistic is when you have more than one predictor variable. I remember I cited an example where a rocket was launched, and the O-ring got damaged, and we tried to look at the effect of temperature on that. Okay, now that's a simple binary logistic regression, because you only have one predictor variable, and of course the nature of the response is categorical. Okay, and I also moved to multiple logistic regression. I remember when we're looking at the effect of smoking habit and age or mortality. Okay, you remember that the smoking habit is categorical. Okay, the age is continuous. You are looking at the effect of each of that on mortality. Okay, that's a multiple logistical regression. And I think I also remember I told you we got three forms of logistic regression model. Okay, we can have a log odd, we can have a odd form, we can also have a probability form. I'm going to say that again. We got three ways to present logistic regression model. Okay, we can present that in a log odd form. We can present that in a odd form. We can also present that in a probability form. And of course, I walk you through that, how you can implement that in R. Okay, and also I remember I said that estimating parameters in logistic regression model, we actually use a method of maximum likelihood. I think you remember that I walked you through that on Thursday. And of course, for simple linear regression and multiple linear regression, we basically make use of a least square method, okay, to estimate parameters in the linear regression model, because the least square method we actually minimize the residual sum squared. I want you to take note of that. Why the method of maximum, likelihood, okay, is what we use to estimate our parameter in a logistic regression model. Okay, so what is new today? Now, what is new today, I basically want to walk you through what I call a time series analysis, which is basically going to be the last topic in the semester. Okay, we're going to this time series, this topic is actually spread over 2 weeks. We're going to do it this week. We're going to do it next week as well. Okay, so I want to welcome you. I want to welcome everyone now to the new topic, which is going to be the last in the semester. Okay, like I said, I'm gonna walk you through this time series analysis, that actually span over 2 weeks. We're doing it this week, we're doing it next week. Okay, now let's get started with time series analysis. I think I need everyone to confirm again. If you are still hearing me clearly, is everyone still hearing me clearly? Before I go into time series analysis now, I want to ask, I need you to ask me a question. Is there anyone who actually need clarification on what we have done so far? Is there anyone before I start time series? I'm going to say this again. Is there anyone who need more clarification or want to ask question about what we've done before I start time series analysis? Is there anyone? Okay, if you feel good, okay, if you feel good, if you really understand, what I've been passing across, okay, I need you to comment yes or you say yes. If you actually, okay, thank you so much. But you know what, if there is anyone who doesn't really understand, please make sure you visit with me during my office hour. If my office hour is conflicting with your schedule, please reach out. Okay, I can actually we can set up a private meeting where I'm actually going to walk you through. Okay, I want to hear from you. Okay, so I want to welcome everyone to time series, but there's something I'm going to tell you. Okay, if you look at all what we've done before up to logistical regression, of course, we have assumptions of independence. We have assumption that observations are independent of one another. Okay, but when it comes to time series analysis, there's going to be a violation of independence. Okay, and that is the reason why we don't want to use regression to actually, explain a time, to analyze a time series data. Because the time series data, of course, there's a violation of independence, and that is the reason why we're actually going to use a time series technique. And that is why it is different from others. Okay, so I want to welcome you to time series analysis. I'm actually calling this part one because we're going to do a lot. I think I have up to part seven. Okay. Like I said, we're going to do, this time series for this week and next week. Okay. I want to welcome you to time series analysis. So what do we mean by time series? Analysis, what do we mean by time series? We're actually referring to a series of observation recorded over time. Okay, I'm going to say that again. The series of observations recorded over time. Okay, now why are we interested in analyzing that? What do we actually want to achieve with that? Looking at the data set collected over time, since we know we live in a stochastic environment, we live in a probability space, we don't expect to collect the same data over time. Like, we don't expect them to have the same value over time. There's going to be variation. I think you know that, right? We basically, analyzing time series data. We actually we are interested in figuring out what the trend is going to be. Okay, we actually want to figure out what the trend is going to be. Are we going to have a stability in the process, or are we going to have an appreciable upward movement or downward movement? Is a movement is going to be downward? Is a movement is going to be upward? Or there's going to be some form of a stagnant in the process? Okay, and that is the essence of doing that. Okay, now, I'm actually I'm showing you now. This is a Mississippi National River. Okay, it's a recreational area. This has been visited, by people. Okay, I'll take a look at the data set I have now. The numbers of visitors in 2011 is 99,398. In 2012, actually rose to 106,733, and that actually decrease, decrease again, and it goes up again. Take a look at that. So what you can see here is actually the numbers of visitors, that have actually visited this Mississippi National River over time. And so this is an example of a time series data. Okay, here year is actually the units, the time index. We could have situation where it's going to be weekly, or it could be monthly, it could be daily. I just wanted to take note of that. Okay, so when I generate a plot now, okay, if you take a look at this guy now, I'm actually plotting this guy against the year. And as you can see, initially it was going up, it get to a point, it come down, and it pick up again, and getting here, it goes down. So if you take a look at that, that is exactly what we expect in this part of, in a probabilistic world. Okay, in a probabilistic world, of course, you expect variation. And you know what, the essence of analyzing time series that are now, like I said, we basically want to determine the trend. Okay, we want to determine the trend. And when you talk about trend, we trend actually measures appreciable upward or downward movement. Okay, we actually need this, the manager of this river, actually need information, to prepare for the future. Because when the numbers of visitors are actually going down, okay, you really want to know what is responsible for that. And if the numbers of visitors is actually going up, you also need that information to be able to plan ahead of time. We find ourselves in a world because of the variation. We need information because we basically want to have control over situation. Okay, so we need information. Now, I'm actually making this to be a time series variable now. Okay, this is the first year. I'm actually going to call that y1. Okay, this is the second year. I'm going to call that y2. Okay, until you get a y8. Okay, so I wanted to, get yourself familiar with the notation that we actually use here. Of course, initially, I think I've defined a time series as a sequence of data. This data set now measure the same thing over time. And the time is ordered. Okay, the same thing that they measure is that we're in 2011, the number here represent the numbers of visitors. In 2012, that still represent the numbers of visitors. So we are actually measuring the same thing over time. Why are we measuring the same thing over time? Of course, there's going to be a kind of variation. We don't expect them to have the same values, but you know what? We're interested in figuring out what the trend is going to be, whether we're actually going to have an appreciable upward movement, or we basically want to have an appreciable downward movement. Okay, we need information. Okay, so like I said, we're basically going to have a y source with t, and that very t is going to be an order time index, just like what you're seeing now. The t can actually be 1, can be 2, and so on like that. And that is what you see. Okay, what that implies is just like we have data set that are collected over time. Okay, in linear regression, the subscript 1 to n, are indices used for, ID purpose. Okay, that doesn't mean the data set are ordered or no. Okay, because you may say that we may use something like that. But here in time series, what we are actually trying to say is that the y1 actually precede y2, and the y2 succeed y1. Okay, so that's what we mean here. So this is being ordered. I just wanted to take note of that. Okay, now I'm going to say in the time series, there are 2 important concepts that I'm actually going to walk you through, that we call the autocorrelation, and there's something that we call stationarity. Okay, but you know what? Just like the way we have assumption in linear regression, we also have assumption in time series, okay, which I'm also going to walk you through. And you know what, in linear regression, intercept model is the most simplest form of linear regression model. Also in time series analysis, we also have the simplest time series model that I'm actually going to call a white noise model. Okay, I'm going to walk you through that. Okay, so I want to have an autocorrelation now. Remember correlation. If you want to can find correlation between the observations at different moment. Of course, the correlation actually measures the extent of positivity or negativity of the relationship between two variables. If you take a look at it now, if I take a YT, okay, the YT is talking about the current, okay, the current value of the series, okay, and the YT minus 1 is talking about the immediate past. Immediate past. I want you to take note of that. 1 is a current, YT is a current, and YT minus 1 is immediate past. For instance, if I want to talk about year now, okay, YT, if I take YT to be 2012, okay, the YT minus 1 is going to be 2011. I just wanted to take note of that. If I want to talk about daily data, okay, let's say today's Monday, right? Okay, so maybe what I record today now, okay, I want to look at the relationship between what I record today and what I recorded yesterday. Okay, the yesterday happens to be immediate past. You get what I mean? Okay, so the why that you basically there's something I wanted to take note. They have one lag apart. One lag, okay, apart. Okay, if you go from YT to YT, if you go from YT minus 1 to YT, we're talking about one lag apart. So when I try to plot that, if you take a look at what I have in each of these plots, which I'm actually going to showcase to you now, okay, that is Y4. I'm going to start from Y1 and Y2, okay, Y1 and Y2, Y2 and Y3, Y3 and Y4, Y4 and Y5 and so on like that. If you take a look at that, you're basically going to see that they're going to have the same correlation. Now, this is a general form of that. Like, okay, when I'm talking about the correlation between Y1 and Y2, or Y2 and Y1, and Y2 and Y3, Y4 and Y5, situation where the lag apart is 1, they're basically going to have the same correlation, which is the 0.65. Of course, I'm actually going to walk you through how you can actually use our software to figure that how. Okay, so that is one lag apart. Okay, so but what of in a situation, okay, what is the difference between that guy and this guy? There's no difference between them. Okay, the YT minus 2 and YT minus 1 is still one lag apart. Okay, maybe I want to talk about immediate past. Okay, maybe I want to talk about immediate past and an immediate past. Okay, immediate past. You get what I mean? Okay, immediate past. Maybe I wanted to talk about yesterday and the day before. Okay, it's still one lag apart. There's a one lag apart between them. I just wanted to take note of that. So it's still going to be the same. Okay, so all of them, we still refer to them in the estimated correlation at lag 1. The difference between them in lag is 1. Take a look at that. We're talking about lag now, the lag apart, the distance apart is actually 1. Okay, between 2011 and 2012, the distance apart is 1. Between 2012 and 13, the distance apart is 1. Okay, between 2017 and 2018, the distance apart is 1. So that's a lag, lag 1. Okay, that's a lag 1 apart. Just wanted to take note of that. Okay, now if I take a stock price, a Google stock price now, and I basically plot the price today versus the day before. Of course, the price today is this. This is the current, right? That is the current, right? Okay. Maybe YT is today, And if you take a look at YT minus 1, okay, this is not immediate past. I'm actually going to call this a day before. Give me 1 second. Okay, so this is a day before. What do I mean by a day before? A day before yesterday. A day before yesterday. Okay, and this is it today, right? That is today, right? What is the distance? The lag apart here is equal to 2. That's that, the distance between that. Okay, that is 2. I wanted to take note of that. Okay, so there's a difference between when you have 2 time series data, okay, and they are 1 lag apart, but this is now 2 lag apart. It's like I'm trying to look at the relationship between the stock price today, and like today is Monday now, right? Okay, relating today with what happened on Saturday. That's a 2 lag apart. That is different from when I'm looking at today and yesterday. When I'm looking at today and yesterday, that's 1 lag apart. When I'm looking at today and the day before, of course, that's a 2 lag apart. So take a look at this. We plotted we plotted that, and of course, we're able to find out the correlation is actually this guy now. So the correlation between today and the day before is actually 0.912. Like I said, I'm actually going to walk you through how you can actually, implement this. And now the correlation here is so high. What does that mean? Or actually mean is that there's a high relationship, there's a positive relationship, there's a connection. That's what we mean. There's a connection between the price of the stock a day before and now. That's exactly what we mean. Okay, so which we call that the estimated autocorrelation at lag 2. You can see that they are 2 lag apart. I just wanted to take note of that. Okay, now I want to go into stationarity now. One of the assumptions in time series is stationarity, but I first want to walk you through what do we mean by stationarity. Okay, what we mean by stationarity, well, assumption is that we don't want mean to change over time. We don't want variance to change over time. When you take a look at this guy now, what is it trying to tell you? Okay, the average, the expected value of y1 equal to expected value of y2. The expected value of y1 is the mean of y1. Expected value of y2 is the mean of y2. Okay, this is more or less talking about the stability. That is the assumption we're going to have. Okay, that's talking about stability. You get what I mean, right? So mean has to be constant over time. Okay, the variance also have to be constant over time. This is more or less looking like an assumption that we have in linear regression, where we said that there's constant variance. Okay, given any values of period, the variance of y is the same. Okay, but here we are actually talking in the realm of stationarity now. Okay, if I want to talk about stationarity, which is the assumptions of time series, okay, we expect the mean to be the same over time. We expect the variance to be the same over time, and not only that, we expect that the autocorrelation only should depend on the difference of movement. What do I mean? At lag 1, okay, the correlation between y1 and y2 should be the same as the correlation between y2 and y3 should be the same as the correlation between y3 and y4. Okay, at lag 1, okay, all the correlation have to be the same. We're actually going to denote that using row 1. Okay, the row 1, okay, row is a notation for correlation. Okay, that's a notation that we actually use for correlation. So anytime you see row 1, okay, it's talking about correlation at lag 1. I'm going to say that again. Anytime you see row 1, okay, that's all mean row. Okay, this guy, I say row, okay, then you see row K, that's a correlation Okay, that's autocorrelation at like K. Now, when you take a look at this, that we said they should all be the same. Now, when you look at it in the formula form, okay, the correlation between YT minus 1 and YT, the correlation between the current and the immediate past, okay, that is a correlation, provided they are like 1 apart, okay, they're all going to be the same. And that was why, what I'm trying to talk about the other time, when I was using the visitors that visited Mississippi River, the correlation between the numbers of visitors that came in 2012 and in 2011 should be the same as a autocorrelation between the number of visitors that came in 2013 and 2012 should be the same as the number that came in 2015 and 2014 and so on like that, provided the two time series variable, are lag 1 apart, their correlation will be the same. That's exactly what we mean. And you know what, not only that, the same thing also applicable, and when they are 2 lag apart, the correlation between Y1 and Y3 must be the same as the correlation between Y2 and Y4. I'm going to go back to the example now. The correlation between the visitor that came in 2013 and 2011 should be the same correlation as the visitor that came in 2012 and 2014. If they are 2 lag apart, the correlation will all be the same. And that's exactly what I'm trying to talk about here. And you know what, symbolically, if you look at the formula, this is the formula now, which is talking about the autocorrelation between the YT, the current value of the process, and immediate past, okay, immediate past, okay, and that is going to be denoted by row 2. Take a look at that. Now, when you take a look, now we can go like, I continue to go like that to lag 3, to lag 4, to lag 5, until we get to the, let's say for lag K, okay, when you take a look at this guy now, okay, the correlation, we're seeking autocorrelation between Y1 and Y1 plus K. If you take a look at the distance between them, they are K apart. Take a look at that. They are all K apart, okay? And if they are K apart, this is a mistake here. That's supposed to be Roy K. So change that guy to Roy K, okay? Because you are actually generalizing now, okay, for K lag, okay? I just wanted to take note of that. Okay, now that you understand that, now the next thing I want to walk you through now, I think I've already gave you what we mean by stationarity, which we call the weak stationarity. The mean have to be constant over time. The variance has to be constant over time. And the autocorrelation, for lag 1, okay, have to be the same across board. For lag 2 up to lag K, I think I just demonstrated that. And you know what? By the time we get to application, I'm actually going to walk you through how you can actually investigate that. Okay, we're still going to do all this in R. Okay, we're going to use an R software. Okay, we have a way to investigate that. Okay, but right now, what I want to walk you through now, how do we identify non-stationarity from observed time series? Because when you have a non, the requirement is that they should be stationary, right? Okay, they should be stationary, right? How am I going to know if they are not? If they are not, then it means that's what we call non-stationarity. So what I want to walk you through right now, okay, how do we now identify the non-stationarity from observed time series data? Let me give you an example of time series data. The time series data you could talk about, the price, the price of gas over time. Okay, the price of gas over time, that price keep changing, right? Okay, that price keep changing, right? Okay, you may want to talk about your volume of sales. Okay, volume of sales, okay, over time. Okay, you could talk about admission. Okay, admission of students into a college. Okay, admission of student into a college over time, okay, is a college going to have more admission, or the admission is going to be going down? Okay, so we have a lot of example. Or maybe I just talking about the volume of sales. You have a grocery store, and you basically want to see whether your sales is going to be going down or is going to be going up. You get what I mean? Okay, so we have different kind of examples of time series data. But you know what I want to walk you through now, how are we going to identify, how can we identify non-stationarity from observed time series data? Okay, you can take data set. If you take a look at what I have now, I plotted, this is what we call a time plot. We call that a time plot. Okay, I'm actually going to show you the coding out, how you can actually do that in out. Okay, this is like, we have some set of values that are collected over time, and I actually plot them against time. Okay, and you can see that, right? Okay, now if you look at the time series, if you look at the variation here and the variation here, they are not the same. And don't forget, one of the assumptions is that the variance should be the same over time. What I'm showing you now, the variance is not the same over time. Okay, the variance seems to increase as time goes up. Look at that. As time goes up, the variance. So in that situation, this is one of the way to identify non-stationarity. Okay, it means the time series is not stationary. It's not stationary, there's no any form of stability here. As you can see, the variance is not the same over time. And don't forget, the requirement is that the variance should be the same over time. Okay, take a look at that. Okay, now another way, if you take a look at this guy now, okay, you're actually going to see here that the mean is not the same over time. We said the other time, the expected value of y1 should be the same and expected value of y2 and so on like that. But here you can see the time series plot that we have now actually indicate that the mean is not constant over time. Okay, the mean appears to go up when time increases. Look at that. Okay, it appears to go up when time goes up. The mean actually goes up. Take a look at that. So which shows that there's a violation, right? Okay, that this is this time series that's supposed to be series. Okay, you can call it that. So that time series is not stationary. Okay, I think I just walk you through now how you can actually investigate whether a particular time series is stationary or not, or using the time plot. Okay, we also have a standard statistical test that we can actually conduct, which I'm still going to walk you through in the subsequent lecture. Okay, so I just wanted to take note of that. Okay, but I want to tell you this. Sometimes the time series plot will mislead us. I just wanted to take note of that because it could mislead, because maybe the number of if the numbers of observation is very small, okay, even though is the data set is basically going to be stationary, is going to tell you it's not stationary. So sample size is also very important, because I'm going to tell you time plot could mislead us in a situation where the sample is very small. Okay, which I'm still going to show you now. Okay, now how are we going to know? Let us pretend. Let us generate. Okay, we're working with this model now. Okay, we already know. Okay, if you take a look at what I said, for example, the following time series YT is stationary according to a population model. Okay, looking at this population model, okay, we are actually assuming stationarity to put on the model. We already know we don't expect the we don't expect any conflict from time plot, okay, because we've already generated this is stationarity. If you look at this population model now, okay, we actually it's a stationarity one. Okay, so we generate a response variable, and from this, we are, here we're actually saying our role. Okay, you're not talking about rho the other time, equal to that. And of course, WT is a white noise. Okay, where the WT as the mean of 0, the expected value of WT equal to 0. Okay, the variance, and we are assuming a constant variance. The variance of WT is 0.19. Okay, we are already assuming a constant variance. We knew, okay, from day one that this should give us a stationary. Okay, it should be stationary. But take a look at that. When I plot this guy now, you see what he's trying to tell me. Okay, the time series only has 50 observations, right? Which is more or less like a small data. Okay, now look at the shape now. Okay, it's trying to tell us it's not stationary. Okay, maybe we need more data set. Okay, and I told you we use this to actually plot this. Okay, and here we have already assumed we are working with a stationary time series model. But look at what it's showing now. I think the reason for this is because the sample is very, very small, 50. What if you collect more observation? Let's see what happened. Oh my God. When you go from, from that to 100, look at 100, you can see some form of stability now, right? You can see a lot of stability now, right? So which means when you have more data set, okay, like initially when I was working with 50, even though I'm using, a time series model that was generated, okay, from, putting a stationarity, under consideration, you can see that when we actually use a small data set, it's trying to tell us there could be some kind of violation of stationarity. But by the time we now move to 100 and we finally move to 1000, you can see it now attains stationarity. So, and that was why I said once we increase the number of observation, we can see that the time series slowly converges to 20. It converges to 20. Okay, as you can see, it converges to 20. Okay, and then stay at the value with small fluctuations. It stay there with little fluctuation, as you can see. That is actually fluctuating around 20. Okay, so the mean and the variance seem to be constant, for time t greater than 40. Okay, when you take a look at time t greater than 40, you basically are going to see that. Okay, so I just wanted to take note of that. Okay, so the increasing trend we see at the beginning is due to an unfortunate starting point, and which means it takes about 40 time period for the time series to climb out of that valley. Okay, so take a look at that. Okay, so therefore, even though YT is stationary, the takeaway, even though YT is stationary, if you're working with a small data set, the time plot is actually going to mislead us to believe it was not stationary. That was what I just demonstrated. Okay, now the next thing I want to talk about now is what we call the error of the time series model, which we call the white noise. Now, it's very, very important. I told you the other time, even when we're dealing with a linear regression, we find ourselves in a world where we want to capture reality with model. Okay, and you know what? The model cannot give us exact reality because there's always going to be an error. Also, in time series analysis, we also have an error component. Okay, take a look at this guy now. We want to talk about the in time series analysis. If error behaves well, we normally call that a white noise. Okay, residual behave well, we call that a white noise. Okay, and here now, what are we trying to say? The white noise actually follow normal distribution with a mean of 0 and the variance of sigma squared. Okay, now take a look at this guy now. Okay, this is an example of a time series model. Okay, I'm basically going to call this autoregressive model of order 1. Okay, Here I'm relating the current value of the series. Maybe this is the current value of the current price of gas in Minnesota, and the YT minus one is probably the immediate pass. Okay, the immediate pass, price. Okay, it now depends on my unit of time. If I'm talking about daily, okay, if it is daily price, of course, maybe the YT could be the price of gas today, and the YT minus one could actually be the price of gas yesterday. If I'm talking about monthly, because the time series could be the time component could be daily, could be monthly, could be weekly, could be quarterly, could be yearly. You get what I mean, right? Okay, so if I'm talking about monthly, okay, it means I'm actually relating the current the price this month, okay, with the immediate past month. Okay, we are in the month of July now, right? Okay, the YT minus one will probably be the price for the last month. You get what I mean? And some of you may be wondering, what is a 0.97? Okay, that is a contribution of the contribution of the immediate past to the current one. Okay, and WT is a white noise. Okay, you get what I mean? Okay, so that's an example of time series, and you know what? That side is actually what we call the deterministic part. You remember in linear regression model, we have a deterministic part, we have a random part. Don't forget, in linear regression model, the deterministic part is actually the explained variation. You remember when I was walking you through the composition of the response variable, right? A response variable, the variation around the response variable can actually be decomposed into explained and the unexplained variation. The unexplained part is a random part. We also have the same in time series analysis, where the deterministic part is basically going to call the signal part. And of course, we also have the random part, the WT, that we actually call the noise. Okay, and you know what we always want to do? We basically want to filter out the noise. We actually want to minimize the noise. And of course, and that is the reason why we got an assumption here that the random part, the residual here, the error here should behave like a white noise. If the error behave like a white noise, what do we mean? It means the expected value of the that will actually be equal to zero, and the variance of that will basically going to be equal to sigma squared. That's exactly what we mean. Okay, is there anyone who need clarification before I go on? Is there anyone who actually need clarification before I go on? I need everyone to confirm if you are still hearing me clearly. So, did you get that? So, is there anyone who need clarification now before I move on? Is there anyone? Okay, so uh, if you really understand what I just explained now, I need you to comment yes, or you say yes. If you really understand what I've been explaining, I need you to say yes, or you comment yes. If you don't understand, please ask question. I'm actually going to explain. Okay, thank you so much for understanding that. Now, like I said, that is similar to linear regression, where that part is, deterministic part, and the other part is a random part. Okay, so, and I call this particular model autoregressive model of order one. Okay, the distance between YT and YT minus one, they are lag one apart. You get what I mean, right? They are lag one apart. Okay, if I'm actually using this to model the daily revenue from an ice cream store, I'm going to say that again. The daily revenue, okay, from an ice cream store. What are we trying to say? Take a look at YT now. Okay, the YT is actually the revenue for today, the current value of the revenue. The YT minus one is the immediate one, like the immediate past, like yesterday. Okay, since we're talking about daily, right? Okay, so if we're trying to fit autoregressive model for that one for that, okay, and probably we know what the row is. The row is 0.97. Okay, I just want to take note of that. Okay, so like I said, the signal part may be 100. Okay, the noise may be 2. Of course, the observed part, which is the current now, so it's going to be 102 when you add that. When you add that up, you get what I mean. Okay, so now I want to talk about. I want to emphasize more on the white noise. You know, the other time I actually said the white noise, in linear regression model, the most simplest form of linear regression model is an intercept model. Okay, in time series analysis, the most simplest form of time series model is a white noise. Let me tell you this. If a time series model is a white noise, you know what it means. Okay, I'm going to say that again. Take a look at that. YT, depending on WT. C here is just a constant, okay? WT, okay, is a white noise, okay? If your model is a white noise, then it means you have an unpredictable situation. It means YT cannot be predicted. That is the meaning, okay? If your model is an entirely white noise, okay? I'm going to say that again. If your model is entirely white noise, okay, then it means you cannot predict in that using that model. Okay, I'm going to say that again. If a model is an entirely white noise, okay, then it means you cannot make a prediction. Okay, you know, like I was talking about the daily revenue of ice cream. Okay, if it is a white noise, what we're trying to tell the world, you cannot predict that. Because let me tell you this. Why am I trying to study time series? Because I actually want to use the variation in the past to explain the variation in the future. I'm going to say that again. You want to use the variation in the past to explain the variation in the future, because looking at the trend, we actually want to make a prediction of what the revenue is going to be in the future. But situation where it is a white noise, where the model is a white noise, you cannot make any prediction. That is what it means. Okay. Now, if you want to try that, okay, I'm going to give you an example of a time series that we actually generate from a white noise. Take a look at this. YT equal to WT. Don't forget, the WT is a white noise. If I generate from a normal distribution with a mean 0, variance 1, I'm going to show you on Friday on how I'm going to show you during the lab session on how we can actually generate that. Okay, so YT equal to WT actually means we are actually we're generating from a white noise, which means it's going to be unpredictable. I'm going to show you an example now. Okay, for similar time series 1, look at that. This is the way it's basically going to look like. Take a look at that. Now I'm going to show you the second one. Okay, the second one are going to look like that too. Look at that. Okay, this is actually time series simulated from a white noise. Okay, now this situation is highly unpredictable. Okay, I'm going to give you an example now. Okay, whether like 1, like 2, and so on like that, I'm going to give you an example now. So in that situation, okay, when you make an attempt to estimate the autocorrelation using the generated data, okay, we actually generate the data set, and we basically want to find the autocorrelation between YT and YT minus 1. That is the way it's going to look like. Okay, you know, when you take a look at this, what you see, the YT and YT minus 1 don't seem to be correlated. They don't correlate. Okay, if they don't correlate, you know the meaning? They don't correlate means there's no connection between them. the prediction will be very difficult to make because there's no connection. Before you can make a prediction, there need to be some sort of connection between the variables under investigation. Situation where it is a white noise, where YT, okay, situation where YT equal to WT, okay, don't forget the WT is a white noise, okay, when you actually generate an autocorrelation plot between YT and YT minus 1, you are not going to have any connection. That's exactly what we mean, okay? Not only, at lag 1, at lag 2, you're basically gonna look at that now. At YT and YT minus 1 at lag 1, you're gonna be the same. At lag 2, there's not gonna be any connection. Okay, even when you continue to go to lag 3, no connection. Okay, what are we trying to talk about? And we actually, before you can actually make a prediction, because one of the purpose of time series is to make a prediction, okay, a situation where the original series is a white noise, then it means there's not going to be any connection between the current and the immediate past, or between the current and immediate past, and so on like that. There's not going to be any connection at all between the current and the previously existing one. And let me tell you, if there is no connection between them, then you cannot make a prediction. It's not possible. That's exactly what I demonstrated now. Look at that. This is purely random. There's no any connection between them. Okay. And of course, this is consistent with the theoretical property of a white noise. Okay, if you look at the theoretical assertion of white noise, is that the YT for a white noise, the YT should be independent from YT minus 1, YT minus 2, and YT minus 3, and so on like that, which is more or less of assumption of linear regression. You know that? Assumptions of linear regression. Observation should be independent. You get what I mean, right? Okay. Observation should be independent. You get what I mean, right? Okay, so that is consistent, right? So in time series analysis, when you have if your model is a white noise, okay, like if your time series variable is a white noise, then there's it means there's not going to be any connection between the current and the past and the previously existing one, which I've just demonstrated here. I just want to take note of that. Now I'm going to give you a practical example now. And this practical example is going to center on Kazim's sleeping pattern. Okay, I'm your professor, and I want to talk about my sleeping pattern now. Okay, suppose the model for Kazim daily sleeping hours, okay, is actually this. What am I trying to say? It's a white noise. That's what I mean. Okay, is a white noise, is YT equal to WT plus 8. 8 is it is a constant in WT, actually from a normal distribution, which means 0 variance 1. Okay. Now, if my daily sleeping hours actually follow that, okay, now I'm going to show you something now. When I plot that, over time, I'm basically going to have this. Take a look at that, right? Okay, I'm actually going to have an unpredictable situation. Take a look at that. Okay, now let us now do this. I want to find the average daily sleeping hours for Kazim. You're assuming this model. Of course, I'm basically going to take the expectation, right? Okay, expectation of both sides. Expectation of a constant, if you take a look at this, that is the same thing as expected value of WT plus expected value of 8. 8 is a constant, okay? Expectation of a constant is going to be a constant. I want you to know that, okay? So the expected value of WT now, okay? The expected value of that equal to that. And what is the expected value of WT if you take a look at this? WT following normal distribution actually means expected value of WT equal to 0. Okay, the variance of WT equal to 1. So this guy is going to be 0, and this is 8. So that's why, so you're going to have is 0 plus 8, and that is basically going to give you 8. And that was how I got this 8. Is there anyone who need clarification? Is there anyone who want to ask question about that? Is there anyone? Okay, so now on average, Kazim actually sleep for 8 hours, right? That is what that guy is trying to talk about. Okay, now what is the variance? Okay, I want to find the variance of this guy now. Okay, okay. Now the variance of WT plus a constant is the same as the variance of WT because C is a constant. Okay. Now, and what is the variance of WT? It's already been given. Okay, the WT follow normal distribution with mean 0 and the variance 1. Okay, take a look at that. So that is a variance. Okay. Now, what is the autocorrelation? The autocorrelation at like 1, at like 2, at like whatever is expected to be 0. You know why it's going to be 0? Because we have a white noise model. Because the YT will be independent of YT minus 1. There's not going to be connection. My sleeping hours for yesterday, I cannot determine my sleeping hour today from that of yesterday. That is what it means. There's no connection because I'm actually using a white noise. I told you when a time series model is a white noise, you know what that means? Then it means you cannot predict. I'm going to say that again. If your time series model is it's entirely white noise, the prediction will be difficult. Okay, you know why prediction will be difficult? Because there's no connection between the current and the immediate past, and there's no connection between the current and the previously existing past. Before we can make a prediction in time series, we basically want to use variation. We want to use the variation in the past to explain the variation in the future. Okay, that's exactly what we're trying to do. And now, whether at row 1, row 1 means the correlation between the two variables that are 1 lag apart is going to be equal to 0, that are 2 lag apart is going to be equal to 0, that are k lag apart is going to be equal to 0. That means there's no connection. If there's no connection between them, then you cannot make any prediction at all. That is exactly what we mean. That is in a situation where the time series model is an entirely white noise. But let me tell you this. In time series analysis, okay, one of the assumption is that the residual should be a white noise. Okay, I'm still going to talk about that. But right now, what I'm trying to talk about is when the entire model is a white noise, because in this model now, there is no signal. I'm going to say that again. There is no signal. I'm going to say that again. There is no signal in this model. We only have a random part, no signal at all. And you know what I mean by signal, right? That's a deterministic part. The deterministic part is missing, and the model here is an entirely white noise. Okay, when you have an entirely white noise model, okay, prediction will be difficult. And of course, this is a demonstration of that. The autocorrelation at like 1, at like 2, and so on like that would be equal to 0, because there's not going to be any connection between the current and the previously existing one. I just talked about Kazim's daily sleeping hours. Okay, if Kazim's daily sleeping hour is entirely white noise without signal, without deterministic component, what that means, it means we cannot predict my sleeping hours. That is what it means. You cannot predict my sleeping hours because there's not going to be any connection between my sleeping hours now and before. There's no connection between them, and that is why I think I demonstrated that to you. When I actually generated a YT from a white noise, okay, and I actually trying to find the autocorrelation of YT and YT minus 1. You can say now there's no pattern, there's no connection for YT and YT minus 2, the same thing, no pattern, no connection, YT minus YT and YT minus 3. So at lag 1, at lag 2, at lag 3, when you continue to go to lag 4, lag 5, and so on like that, there's not going to be any connection at all. Okay, that is a situation where the time series model is an entirely white noise without any signal or without any deterministic part. Oh my God. So which means now the question now, is this model consistent with common sense? Okay, that's a question we're going to have. Is it consistent with common sense? We want to make use of common sense. I want to say it's not consistent. How can you tell me my sleeping hours, is unpredictable? Okay, it doesn't make sense at all. Okay, so which means, I'm going to tell you, Kazim's daily sleeping hours, is not it can actually be predicted. So it's not a white noise. Okay, it's not a white noise at all. So what determines my sleeping hour, that actually depends on the numbers of hours I slept yesterday. If I want to determine the numbers of hours I'm actually going to sleep today. Okay, so and that was why I asked a question on whether this is consistent with common sense. You get what I mean? Okay. Okay, okay, so this is where I'm actually going to stop today. Today, I introduce you to time series analysis, part 1. Okay, is there anyone who need clarification before I go today? Is there anyone who want to ask question before I go today? Okay, I want to appreciate every one of you who have attended my lecture today. I hope you guys enjoying it. Like I said, I've not been seeing students in my office hour. If it is conflicting with your schedule, please reach out. Okay, if my office hour is conflicting with your schedule, please reach out. But my office hours still hold, the on the day that I actually specified on the syllabus. I think I have somebody want to specially meet me tomorrow. If you also want to meet me tomorrow, there's no problem. You can meet me at 11. Okay, even though Tuesday is not listed. Let me see. Oh yeah, Tuesday is listed. Okay, Tuesday is listed too. And if my office hour is conflicting with your schedule, please reach out. I can meet you. We can actually set up a special, meeting. Okay, in case you need a clarification. Okay, like I said, I want to appreciate everyone today who have attended my lecture. The recording is basically going to be published as issuer. Okay, make sure you stay safe and have a lovely.
For the
Okay,
is
go
the
ahead.
exam is the exam this Friday?
Yep, it's gonna be this Friday, and of course, as issuer on Wednesday, I'm actually gonna walk everyone through the practice question, and today I'm gonna upload the practice question for the midterm. Does that make sense to you?
Yeah.
Okay, so the exam is still Friday, like the way that I'm going to upload, just like the way we did in the midterm one, where I upload exam one day and it's going to be left open for 24 hours. You also are going to have opportunity to start with at any time within the 24 hours window. So like I said, I'm flexible because I know some of you work. Okay, is there any other person that want to ask question before I go? Is there any other person that will ask question before I go? Okay, in the absence of question, make sure you stay safe and have a very lovely day. So bye for now, everyone.